Okay, get this. What if a neural network could do more than just crunch numbers? What if it could heal itself, adapt, maybe even find its own sense of balance? It sounds like science fiction, right? Well, that's exactly the groundbreaking vision we're digging into today, and it all comes from the mind of researcher Anthony Pyper. All right, so first things first, let's talk about the big problem. All the incredible AI we use every day, the language models, the image generators, they are insanely power hungry. We're talking about a massive drain on memory and processing power. It's becoming a real crisis, actually, because it's holding back where and how we can use this amazing tech. And that's the exact problem Anthony Pyper decided to tackle. So this brings us to a pretty radical question. Instead of just throwing more and more power at the problem, making our models even bigger, what if we looked somewhere else for inspiration? Like, say, biology. What if we could build an AI that acts more like a living thing, one that can heal itself, adapt to change, and find its own balance? That is the wild idea at the heart of this entire framework. Okay, let's really dive into this hidden crisis. Because, the power and memory thing isn't just a minor headache. It's a massive wall blocking real progress. I mean, just look at the difference here. On the left, you've got your traditional AI. Yeah, it's incredibly precise, but look at the cost. It's off the charts. That makes it totally useless for smaller, everyday devices. Think sensors or any kind of smart hardware on the edge. The whole goal of this project was to create an AI that could operate in that tiny little bar on the right. That's a huge leap. So, the big question is, how on earth do you get that kind of efficiency? Well, the answer is nothing short of a revolution. It's about completely rethinking the basic building blocks of a neural network. Welcome to the one-bit revolution. And here it is. This is the aha moment. On the left, you see a typical weight from a neural network. It's a super precise number with tons of decimal places. That takes up a lot of memory. But on the right, this is the one-bit approach. Instead of that whole long number, a system like bit-net linear just stores the sign. Is it positive or is it negative? That's it. A +1 or a -1. Just that one tiny change, it absolutely slashes memory usage to almost nothing. Now, the fancy technical term for this is quantization. A good way to think about it is like taking a super high-res 4K color photograph and turning it into a simple black and white sketch. You lose detail, but you keep the essence. But here's the thing. Most research just tries to simplify things a little bit. This framework, it takes it to the absolute logical extreme, crushing everything down to a single, solitary bit. Okay, but wait, there's a catch, right? If you're just tossing out all that information, how can the network possibly be any good? That's the big challenge. And the answer is where the next layer of genius comes in. You have to make these super simple neurons incredibly resilient. You have to make them, well, almost lifelike. So to make up for losing all that data, Anthony Pyper designed something he calls the liquid metal neuron. This thing is amazing. It's not just doing one-bit math. It has thermal sensitivity, it can adapt its learning, and this is the really cool part. It can actually repair itself using saved or cached states. And that's the key takeaway here, right? The extreme simplicity of one bit is balanced out by adding these incredible layers of biological-style resilience. And check out how this self-repair actually works. Let's say a neuron gets damaged or its state just goes haywire. Normally, that'd be game over, but not here. Instead, it can literally reach back into its own memory, its cache, pull up a previously good state, and just restore itself. It's an absolutely fundamental feature, and it's what gives the whole network this amazing stability. But, clever engineering will only get you so far. To really guide the behavior of a network this simple, the framework adds another layer, and this one is almost philosophical. This is the part that elevates it from being just a tiny calculator into a system that is actively searching for balance, for harmony. It's all built on an idea called the Fundamental Triad. And the first part of that is the monad. You can think of the monad as the perfect state, right? It's total unity, total coherence, a point where the system is perfectly, beautifully balanced. But let's be real, perfect balance doesn't last forever. So from that unity, you get duality. And duality is all about division, opposition, conflict. Basically, it's the problem that needs to be solved. It's the state of imbalance that the system has to figure out. And that brings us to the third part, the triad. The triad is the resolution. It's the process of taking all that conflict from the duality state and finding a new, stable harmony. So you have this constant cycle. Unity, then conflict, then resolution. And that cycle is what drives the whole system forward. Okay, so we have these abstract philosophical ideas. How do they actually get put into practice? Well, this is where things get really wild and where the system starts to act like a living, breathing thing. It all happens in this continuous loop. First, there's a sort of quantum-like transformation that makes the energy of the states fluctuate. Then, the liquid metal network gets to work, processing those states and updating their harmony score. And finally, the system decides which state to transition into next. It's just this constant dance of change and rebalancing over and over again. And here's something that is just so cool. The system can actually break its own states apart into smaller pieces and then put them back together in totally new combinations. This whole idea is pulled directly from biology. It's how living systems break down and rebuild themselves to get stronger and more resilient. I know. This all sounds super abstract, maybe even a little out there. But the big question is, does it actually work? Well, the demonstration shows that yes, it absolutely does. And it could be paving the way for a whole new future of lightweight AI. If you look at the results from the test run, it's pretty clear. Over 30 cycles, you can see these key measurements like harmony, which is basically its internal balance, and integration, how well everything is working together. They both level out and become stable. This is the proof. It shows how resilient the system is. Even with all this chaos happening under the hood, that fundamental triad holds steady. So what's the bottom line here? Anthony Pyper's one-bit liquid metal neural network. It's not just some cool idea on a whiteboard. It's a real, functional blueprint for a completely new kind of AI, one that is unbelievably efficient, seriously adaptive, and built on the very principles of life itself. And that leaves us with a really powerful thought to end on. You know, for decades, we've tried to make AI smarter by just feeding it more power and more data. But maybe the real breakthrough isn't about being smarter, but about being more resilient. If we can teach an AI to heal itself and find its own balance, what else could it learn from the playbook of life? And remember, this entire incredible framework, from those tiny one-bit neurons all the way up to that philosophical triad, it's all the work of Anthony Pyper, who is truly pushing the boundaries of what we thought a neural network could be.